right, awesome, Mrs. Larkin. Perfect. We're going to actually put it up because you've accomplished it. It is 11:30. We are going to begin. Thank you, everybody. This is excellent. We are not dentists. We don't like pulling teeth. So please make sure that you get your content question. Perfect job. Excellent. High five to y'all. So let's take a look at this. We're going to box the properties generally related to acids. So again, we talked about this yesterday. So acids, remember, vinegar, orange juice, lemons are examples of those acids. Remember, they have that sour taste. Okay, they have that sour taste, and they turn litmus paper red. We talked about that blue for base, red for acid. Okay, and they corrode active metals. Okay, they corrode those active metals. And then finally, this is the important part, important characteristic or property of an acid is that it increases the hydrogen ions in a solution. So they give up those hydrogen H plus ions in a solution. Okay, excellent job. Nice job, everybody. So jumping over here, do you prefer friends who are very similar to you or very different from you? And I like the answers similar, but also kind of a little different. Definitely similar. Yeah, we kind of gravitate towards people who are like us, but we also like people that are kind of different, right? That whole idea and what we're talking about in physics right now, opposites attract, that whole saying of opposites attract, we do have that kind of saying. And so we kind of like people that are similar, but we also like people that are different. I like Amaze up there, different. Yes, awesome. So let's go ahead and move on. Remember, Class Connect sessions are recorded and distributed for learning purposes. Please do not put any personal information or information of others into the chat box for your protection and the protection of others. All right, so let's go ahead, and if you have your attendance up, again, we give you the first 15 minutes of class to get your attendance. If you technically have until midnight tonight and you were able to get your attendance for the full class today, nice participation. Thank you so much. Go ahead and scroll up for those links and raise your hand once you have gotten your attendance in. This should be pretty fast because a lot of you were able to get going and participate, and you were given your attendance a little bit earlier. So go ahead and raise your hand once you have your attendance in. I'm going to give everybody a total of 20 seconds to get that in. Go, go, go. Again, the start of the class word is in the chat box. The links, you just need to scroll up for those links. Again, try both of them if you're unsure which teacher you are. When we only have 6 days left of class, that's All right, here we go. Kamari, Ira, Jaden, Tim, Patrick, Christopher, May, Eric, Peyton, welcome in. Go ahead and raise your hand when you have that attendance up. Thank you. Aria, Patrick, Christopher, Eric, and Peyton. Peyton, Eric, Christopher, Patrick, let's get it. Thank you so much. Aria, Eric, and Peyton, you're my last 3. Aria, Eric, and Peyton, you're my last 3. Let's go. Hands up, hands up. All right, here we go.
All right, everyone. So this is a reminder, we only have 6 days left of the trimester. Obviously, you will have some time to work over the weekends as well. The trimester does end on Wednesday, the 3rd of March, and all of next week, you will have to work on anything that is missing. You should be focusing on projects, the final exam, as well as any notes. Notes will help to boost that project and final exam category as well. So those are the things that you should absolutely be focusing on. Hi, Omar. Make sure you grab your attendance, scroll up for the links. Start of class word is in the chat. Today we're going to be taking a look at acid-base reactions. Tomorrow is our last lesson of the trimester. We'll be talking about titrations. Thursday you will have a recording that goes over the first half of the final exam. Friday, we will go over the second half of the final exam in class. So if you watch the recording on Thursday, and if you come to class on Friday, you will do very well on the exam. Historically, students have always done very well on the final exam as long as they do what we ask them to do, which is watch the recording, come to class, and make sure that they are participating. Just as a heads up, that's what you need to do to be successful as we go into our last big assignment of the trimester. Here we go.
So as you can see, acids and bases, there's a short unit. We only have just one more thing, titrations, which is tomorrow. No more new content, and then we jump into that final exam that Mrs. Larkin just talked about. So let's go ahead and discuss what we're going to be doing today. We're going to define pH and explain how to use pH to identify acids and bases. We're going to explain the different components of neutralization reaction and explain how buffers resist changes in pH and identify various buffers in that. So, and then we're going to do this with our 5B notes with an 80% or higher, which I know you'll do so much better with. So with that, let's go ahead and open up our notes. Your links are provided for you in the chat box. Make sure you open up that link, start your quiz, and raise your hand. If you are watching the recording, scroll down or go to your grades tab, scroll down to 5B notes and start your quiz. I'm going to give everybody about 20 seconds to do that. 20 seconds. Go, go, go. 4 seconds. Let's get 100% of participation. So still looking for Michael, Monty, Aria, Jaden, Tim, Patrick, Eric, Omar, Kale. Go ahead and raise those hands. Raise those hands nice and high. Kale, Omar, Eric, Omar, you in the chat box? Awesome. So Kale, Eric, and Monty. Eric, Monty, and Kale. Let's raise our hands. I'll be checking in with you 2 or 3. Here we go.
All right, so let's go ahead and take a look today at the pH scale. So we are going to be talking about the pH scale, which helps us to identify if liquids are acidic, basic, or neutral. Now, the thing about the pH scale is it has to do more with how far things are from the middle. So I know it's kind of confusing to think about, but you want to think about what's in the middle and how far away are we from the middle. So in the middle, we have a pH of 7. That is neutral. That is going to be like water. It's neither acidic, neither basic. It is neutral. Now, the further away you get from neutral, the more extreme you can become. So over here on the left, we have the acids, and as we get closer and closer to these small numbers, less than 7 numbers, so 1 and 2 and 0, those are going to be the most acidic chemicals. Over here on the right, as we get closer to 14 and 13, those are going to be the most basic chemicals. If you're kind of on the acidic side, but like close to neutral, that just means you're slightly acidic right here. Or if you're on the basic slide, but again close to neutral, that just means you're slightly basic. All right. So again, the extremes are what we care about versus the being close to neutral in the middle. Now, a good way to remember this is we learned already that red litmus paper, red turns red, or red stays red, blue turns red. Red means acidic. So I'm going to call this the red side of our scale because we can see more red colors or colors that are like red, orange, and yellow on the acidic side. And I'm going to call the basic side the blue side, B for blue, B for basic. That's the side with blues and greens and purples. All right, go ahead and give me a smiley face emoji in the chat box if this scale is beginning to make sense. You're going to have to match these up in just a few moments. I'm going to go over some examples. Excellent. All right, so again, water is neutral. As we move a little bit further away from water, we get to slightly acidic, slightly basic stuff. So an example here is urine. Urine is on the acidic side. It's on the red side, but it's still pretty close to the middle. So this is just slightly acidic. So we can go ahead and write that right here. This is slightly acidic up on the board here, okay? Same thing if we move the opposite direction, we're going to end up with something that is slightly basic, slightly basic, like human blood. Human blood has a pH of 7.4, so it's definitely bigger than 7, so it's on the blue side, on the basic side. But again, it's still really close to 7. Obviously, it's really close to water, so it's just slightly basic. Taking a look here, tomato juice is a little bit more acidic. Hand soap is a little bit more basic. And then at the extremes, the furthest to the outside, we have things that are very acidic, very basic. So gastric acid in your stomach is extremely acidic with a pH of 2, whereas bleach is extremely basic with a pH of 12. So again, closer to the middle, less acidic, less basic. Further from the middle, more acidic, more basic. Exact middle is neutral. Let's make sure that we understand these. Go ahead and match these up for me on the board.
Have your whiteboard tools, just like Mrs. Larkin said, go ahead and match these terms with the definition of neutral, slightly, highly acidic, or basic. Because of your pool. That's awesome there, May. Yeah, exactly. Exactly. You always have to take the pH of your pool because you want to make sure it is where it needs to be. I'm not too comfortable with the pool situation, not a pool man or a pool lady. Excellent. Going to give you another 5 seconds. 5 seconds to go. Beautiful. All right, I'm going to go ahead and put our whiteboard tools on hold. Thank you so much. Fix urine, please. Yes, please fix urine. Please, please, please. All right, let's go ahead and take a look at this. Make sure we go through it. This is going to be the answers to number one, but let's take a look at this. So human blood has a pH of 7.4. So that is going to be slightly basic, slightly basic. So it's going to be over here, right here, right around here. Okay. So gastric juices, which has a pH of 2, is going to be highly acidic. So if it's right here, it's going to be highly acidic. Whereas human urine, pH of 5, is going to be slightly acidic. Slightly acidic right here. And obviously coming down here to bleach, highly basic at 12. Highly basic right here. And then water with a pH at 7, great middle point there, is going to be neutral, All right, these are the answers to number one. Go ahead and lock in your answers. I'm going to give you 25 seconds to do that. Go, go, go. Raise your hand when you are finished. Raise your hand when you are finished. Box, excellent. 10 seconds. 10 seconds. Again, if you need more time, take a picture and then raise your hand. You can always complete it a little bit later. All right, so I'm going to go ahead and check in with a few people. Kamari, Annabelle, Tim, Patrick, Christopher. Woo, we're moving, so good job. I see you in the chat box, Omar, Skylar, Eric, Christopher, and Tim. Tim, Christopher, thank you, Tim, Christopher, Eric, last call, Eric, I have not heard from you, Eric, excellent. All right, so I'm just looking for Christopher and actually just Christopher. Beautiful, thank you so much.
So let's go ahead and talk a little bit about what pH actually means. So pH means hydrogen potential. Essentially, all pH is doing is measuring the amount of hydrogen cations, those positive hydrogens in solution. And that should make sense because remember, positive hydrogens are what acids release. So more positive hydrogens, more acidic. Less positive hydrogens, definitely then less acidic. Now, I know this is a little bit confusing, but the math behind pH actually results in low pHs, meaning high amounts of hydrogens. So I know that's a little bit confusing, but you should still know that both of these are true. You should know that pHs of 0 through 6 give us acids, right? So that's a low pH. And you should know that high amounts of hydrogen in general mean that we have acids because acids release hydrogen. So I know low pH, high amount of hydrogens is kind of opposites, but this should still make sense that these are acidic. Give me green checks, orange X's if that's beginning to make sense. That's kind of something that you either just need to remember, low pHs are always acidic, lots of hydrogens means acids, or you just need to remember that they're opposites. Excellent. All right, same thing here. That high pH, right, pHs of 8 to 14 are definitely basic. That's the blue side of our pH scale, but this actually calculates out to a low amount of hydrogen. What it actually is it is that bases are releasing lots of OH negatives, hydroxide ions, so they definitely have less hydrogen ions. Mrs. Sepulveda is going to go ahead and send out the attendance one last time, and then it will be erased from the chat in a minute. All right, this is going to be number 2. Please go ahead and fill in the blank with the word concentration. Only the word concentration. Make sure you spell it correctly. You have 20 seconds to raise your hand. Go, go, go. All right, just waiting on Michael. Kamari, Annabelle, Jaden, Christopher, Anthony, Omar in the chat, Omar, Kale. Thank you, Alexis, awesome, Omar, I see you in the chat. Again, we're just waiting on Chris and Anthony. I'm going to clear out the chat with our attendance. Sorry, I have to erase your spider there. All right, let's go ahead and keep on moving, everybody. All right, so let's talk a little bit about this idea of indicators. So again, we learned about yesterday litmus paper, that there's red and blue litmus paper, and depending on which colors they change, that tells you if you have an acid, base, or neutral, right? We said if your red paper stays red and your blue paper turns red, red and red means acid. If your blue paper stays blue, your red paper turns blue. B for blue, B for base, so blue, blue, base. And if they don't change, red stays red, blue stays blue, then that must mean it's neither acidic, neither basic. That must mean it is neutral. However, that's not super specific. We've learned now that there are specific pHs all the way from 0 to 14, but our litmus paper only tells us, is it an acid, base, or neutral, not how acidic, not how basic. So instead, we need other indicators. So pH paper, which I am going to show you an example of today, pH paper actually has lots of indicators in it that can change lots of different colors. So based on these different colors, we can get a much more specific value of what the pH is. So for example, you can see here car battery acid is very, very acidic with a pH of 1. Water, again, is neutral. You can see that right here. And bleach, all the way over here, is going to be very, very basic. Just so you know, it's really hard to get things that are pH of 0 and pH of 14. Those are extremes. Very acidic, very basic. So most of our examples fall between the like 2 to 12 range, just so you know. Yeah, we don't want acids. Even bases can melt your skin off. So severe acids, severe bases can both injure you. So we want to be careful with this. So let's go ahead and take a look at pH paper in action. So what we're going to do is I'm going to test 3 different substances, and you are going to figure out, is it acidic? Is it basic? Is it neutral? And then how acidic or how basic? Is it highly, slightly acidic, or highly, slightly basic? Let's go ahead and take a look at this. I'm going to go ahead and pop this up on the board for us. All right, so we're going to go ahead and start off with water, because water is our easiest one. All right, so here is my water. All right, I'm going to go ahead and dunk this in. And then I want you to go ahead and tell me, what color do you see this? What color is this? Go ahead and tell me in the chat, what color did it turn? Yeah, it turned green, kind of a light green. Again, if you could see it, which is, I know it's hard for you to see it, but what I'm seeing is that it matches up very well with the color that is under 7. And so this has a pH of 7, and it's water, so we know pH of 7 means what? Acidic, neutral, or basic? pH of 7, what does that mean? Yeah, it's water. We know water is neutral. That one's easy. That's a gimme. Here we go. No, it's just tap water. Special water. What is special water? All right, let's go ahead and now try out vinegar. All right, so this is my vinegar right here. You can go ahead and dunk this in. And same thing, go ahead and tell me, what color does that vinegar appear to be? What color does this vinegar strip appear to be? Yeah, this is orange, kind of yellow. I would call it macaroni orange. Again, I'm looking here. This is kind of a pH of like 2 or 3, pH of 2 or 3. So if it's a pH of 2 or 3, that puts it on the red side of our scale, the low side of our scale. So does that mean it's an acid or a base? So if it's on the red side, the low side, red, red, low side, is that an acid or a base? Definitely an acid. Now specifically, if it's kind of like 2, that's pretty close to 0. It's pretty far away from 7, far away from neutral. So does that mean it's highly acidic or slightly acidic? If it's far, far away from neutral, is it highly or slightly acidic? We know it's an acid, but how much of an acid? Yeah, it's going to be highly acidic. All right, let's go ahead and try our last thing here. This is just baking soda dissolved in water. I know you can't really see them, but here's my baking soda. I dissolved that in water earlier. And let's take a look at this pH. I'm going to go ahead and dunk that in for us. And what color did this one turn? Yeah, dark green. Last time we had light green. This time this is dark green. Again, I'm going to match this up, and this is kind of between 8 and 9. Between 8 and 9. So this time it's on the higher side, more towards the blue side. So blue, B for blue. What is this one? What is this one? B for blue on the bluer side. Awesome. I see Omar, I see Shelbs, I see Miles. B for blue, B for base, B for base. Now specifically, if it's at 8 or 9, all right, that means it's still pretty close to 7, still pretty close to neutral. So does that make it highly basic or slightly basic? If it's still pretty close to neutral, is it highly basic or slightly basic? Yeah, exactly. I see Shelbs, I see Camilla working in the chat. Again, it's still pretty close to neutral. That means it's only slightly basic. So it definitely is on the basic side, but still pretty close to water, so only slightly basic. If I stick my hand into baking soda water, it's probably not going to hurt me. Baking soda water, interestingly enough, is what you boil your pretzels in at home. In the industry, they actually boil them in a lye solution, and lye is sodium hydroxide, which we talked about is very basic and can be very dangerous. So when they use them in restaurants, they have to be very careful when they use that solution. But at home, we don't use lye for please don't use Drano for your pretzels, but you can use baking soda in water. Awesome job, everybody. Let's go ahead and give me once my PowerPoint comes back, here we go. Go ahead and give me a green check, orange X if it makes a little bit more sense now that you've seen pH paper in action. Yeah, lye is used in soap, lye is used in Drano, and lye in very, very controlled situations can be used for pretzels. But please do not do that at home. Do not use soap or Drano on your pretzels. That can kill you. Okay, probably not the soap, but the lye definitely can. The Drano definitely can. All right, looking good. I see lots of green checks. Let's go ahead and keep on moving here. All right, so now we're going to go ahead and talk about this idea of opposites. At the start of class, we talked about friendships, and some of us said that we like friends that are different from us. Well, acids and bases are extremely different from each other. Talking about the most common examples, yesterday we took a look at hydrochloric acid, HCl, a very strong acid with a pH we are learning today of 2. Sodium hydroxide, NaOH, again lye that we just talked about, Drano, is a very strong base with a pH of 13. So very acidic, very basic. They by themselves are very corrosive and dangerous. You do not want to get hydrochloric acid on your skin. You do not want to get sodium hydroxide, lye, Drano on your skin. You want to avoid those. They can both be corrosive. They can both dissolve your flesh. All right, so we do not want to use those without like gloves and appropriate precautions. Okay. Yeah, I mean bleach, yeah, you don't want to get a lot of bleach on your hands, but bleach is definitely less basic. So I got some bleach on my fingers earlier today and it didn't kill me obviously, but I'm going to wash my hands as soon as that happens because it begins to make your fingers sting. Yeah, yeah, exactly, Shelbs. All right, now the cool thing though is when you do mix them together, you actually get a neutralization reaction. They actually neutralize each other. We can see this root word here of neutral. Neutral meaning neither acidic, neither basic. It's neutral, it's in the middle. Let's take a look at how that happens. So again, sodium hydroxide is a base and bases provide OH ions. Hydrochloric acid is an acid and acids provide hydrogen ions. And these two things are going to attack each other. Okay, so now I have an O, an H, and an H. That means I have 2 hydrogens, 1 oxygen. What does that make? 2 hydrogens, 1 oxygen. What does that make? Thank you, Shelbs. I see you in the chat. H2O makes what? H2O makes what? Yeah, it just makes water, right? So you can see right here, we end up with water, and water is definitely neutral. All right, so we have something that is our, right here, again, we have our, where are you going? This is our base, and we have our acid right here, okay? Now, the other stuff is also going to go ahead and then bond together because it's like, hey, I lost my friend, I'm going to go find another friend. So that means sodium is going to then go ahead and hook up with this chlorine that is now by itself. So they are going to now become friends, and that is going to result in sodium chloride. Now, all neutralization reactions result in water and salts. So this right here is a salt. Specifically, this is a salt that we can eat. Not all salts you can eat. Please don't eat all salt, like the salt that goes on the road. Please don't eat that. But this table salt you can eat in small amounts, right? So table salt NaCl is also formed here. Now, what I want you to think about is if I have a strong base and a strong acid, do either of them win? Think about if I have two really strong people in a tug of war, does anybody really win? If they are equally strong, does anybody really win? Yes or no? Does anyone win in a tug of war if everybody's equally strong? No, nobody wins. And so that is why this salt right here ends up being what we call a neutral salt. All right, so this is a neutral salt. All right, because the acid and the base, nobody won. It just ended up with a neutral water and neutral salt. Go ahead and give me a smiley face emoji in the chat box if you're beginning to feel comfortable with that. We're going to then talk about what happens when you have different strengths of acids and bases. Let's jump into it. All right, so this time let's think about what happens if we have a strong base with a weak acid. So sad. Let's take a look here. So we have a strong base here, which is sodium hydroxide. Again, it's going to provide OHs. And we have a weak acid here, acetic acid. That's just the chemical term for vinegar. Just so you know, all of the food that you eat is made up of chemicals. You are made up of chemicals. So when people say they don't eat chemicals, they're being silly because all food is chemicals. All right, anyways, so vinegar right here is acetic acid, and it's going to donate its hydrogen. Acids donate hydrogens. And together, OH and H give us our water. So we can see our water right here. Again, definitely neutral, pH of 7. However, again, the other stuff is now left by itself, so it's going to go ahead and bond with each other. So this sodium is going to go ahead and bond with this acetate right here. All right, and we're going to go ahead and end up with sodium acetate, and this is going to be our salt. This time, though, it is not a neutral salt. Just so you know, this is the salt that flavors salt and vinegar chips. I think we talked about that earlier in the trimester. But this is actually not a neutral salt. Let's think about this. If I have a strong base with a weak acid, who wins, the base or the acid? Who wins the neutralization? The base or the acid? If I have a strong base with a weak acid, strong base with a weak acid, who wins? Who wins the tug of war? It's literally in the words, who wins? The strong one wins, so the base wins. Does that make sense, Shelves? So the one that is stronger will win this tug of war in the neutralization reaction. So our base will win, and the result is we end up with a slightly basic salt. All right, it's not super basic. It is a neutralization reaction, so it's still close to neutral, but it is slightly basic. Go ahead and give me a smiley face in the chat box if that makes sense. Smiley faces in the chat box if that makes sense. So we end up with a slightly basic salt, slightly basic. Perfect. All right, let's go ahead and try the other one then. What happens, do you think, when we have the neutralization of a strong acid with a weak base? This time, who wins? Strong acid, weak base, this time who wins? Yes, this time our acid wins. So this time we actually end up with a slightly acidic salt. All right, so an example here is ammonium hydroxide, which is found in Windex. All right, with hydrochloric acid, that's our strong base. So this one is weak base. This one is strong acid. Okay, so taking a look here, our weak base will donate OHs. Our strong acid will donate H's. That just ends up being water. Again, that is definitely the neutral part of our neutralization. On the other hand, everything else is going to make the salt, right? So we can see NH4 and Cl are going to now go ahead and bond together to make ammonium chloride. This ammonium chloride, again, is going to be slightly acidic because in the tug of war, the strong acid will win. So slightly acidic. Let's make sure that this makes sense. We're going to go ahead and do a check for understanding. Here we go. Oh my gosh, Ame, please do not do that. Here we go.
Strong base, weak acid, strong base, and obviously give what is the definition? What is the neutralization? Strong acid, weak base. I'm going to give you 15 seconds. Here are your whiteboard tools. Go ahead and take a look at this. Match those up with the definition of either acidic salt, neutral salt, or basic salt. We just did the examples right now. This should be pretty easy. 2, and 1. All right, let's go ahead and put our whiteboard tools on hold. And yeah, you guys did a pretty good job here. Excellent. So let's go ahead and take a look at this. This is obviously going to be the answer for number 3. As I go through this, lock in your answers and raise your hands. So a strong base, weak acid is going to be a basic salt. Remember, in that tug of war, who's going to win? And then obviously looking over here, strong acid, strong base, they're going to equalize each other out, and so that's going to be your neutral salt. Whereas the strong acid and weak base, again, tug of war, who's going to win? Strong acid is going to give you your acidic salt. So kind of be aware of those, which is stronger, which is not in that tug of war. And then obviously if you both have a strong acid, strong base, you're going to neutralize each other out. So go ahead and raise your hand. I'm going to give everybody 20 seconds up on the clock. Here we go. Go, go, go. All righty. So Michael, Kamari, Tim, Patrick, Skylar, Adriana, Omar, I see if you're in the chat box. Omar, let me know if you're in the chat box. And Tayan and Alexis. Raise your hand. Awesome. Thank you, Omar. So Patrick, Skylar, Tayan, please raise your hand. Tayan, Skylar, Patrick. Thank you, Patrick. I see you up there. 2 more, Skylar, and Tayan. Skylar and Tayan. All right, here we go.
All right, so the last thing we need to talk about today is buffers. Now, buffers, you probably have heard this term before at some point in your life. Buffers are things that kind of prevent chaos from happening, right? If you're a buffer between 2 friends who don't usually like each other, that means that because of you, those friends can spend time around each other because you are buffering the situation. So in the same way, buffers are solutions that resist pH changes when you add too much acid or base. So they try to keep a solution as close to neutral or as close to a specific pH as possible by neutralizing any additional acid or base, right? So they're going to resist pH changes. Now, the reason buffers are so special is because they're made up of a mixture of both a weak acid, which we're going to represent here as HA. The H is obviously the acidic part, and then the A is just a representation of any weak acid. It's not a real chemical. A is just a pretend chemical there. And it's a mixture of the weak acid with its opposite, conjugate, we call it conjugate, weak base. And this weak base has lost its H+, and so now we're just left with a minus. All right, so it's got both the weak acid and the weak base, and we'll talk about why this works so well in just a moment. Please go ahead and fill in number 4 first with the word resist and only the word resist. You have 20 seconds to raise your hands. Go, go, go. 10 seconds, raise your hands. All right, I am waiting for Kamari, Jaden, Timothy, Skylar, Anthony, Omar, Tayan, Kale, and Alexis. Please raise your hands if you have your number 4 done. Thank you, Timothy. Waiting on Kamari, Jaden, Anthony. Omar in the chat is good. Tayan, Alexis. Tayan, Alexis, thank you. Tayan. Kamari. Tayan, Kamari. Tayan, hello. Tayan, last chance, hello. Tayan. Kamari, are you there? Hello, Kamari. All right, we're going to go ahead and check in with you, Kamari. Please make sure that you are responding. Here we go. All right, so let's talk about why this works. So here's the deal. In our buffer, again, we have our weak acid, which is HA, and our weak base, which is a negative, the opposite. Okay, so that's going to be important for later. Now, if we have our buffer solution and we try to add a strong base, again, strong bases are going to add OH negatives. Okay? Now, the weak acid is our HA. It is going to then react with this strong base right here. Okay, so that makes sense. The opposite thing should react. I add a strong base, the opposite weak acid should react with it. And the way that it does this is it gives up its H's, right, its hydrogens, to bond with those OHs. And HOH just makes what? HOH just makes what? 2 H's, 1 O, 2 H's, 1 O just makes what? Yeah, it just makes water. So here's where that water ends up. So that seems to make sense, right? That's definitely just neutralizing it. We end up with some neutral water. Perfect. However, there is still something that is left over. Take a look right here. I am actually left over with this A by itself. So now I have an A minus here. But A minus is something that we already have in our buffer. Let's go ahead and read the board and tell me in the chat box, A minus is our what? Read the board where I am pointing and type it in the box. A minus is just the what in the buffer? Yes, it's just the weak base. So what we did is not only did we neutralize a lot of it and turn it into water, but we also just created a little bit more of our weak base. So essentially what we did is with our weak acid, we were able to turn a strong base into a weak base. Smiley faces emojis in the chat box if that makes sense. So with the opposite weak acid, we turned our strong base into a weak base. Now, this again is going to make our pH slightly more basic, right? Slightly more basic, but definitely not as basic as if I didn't have the buffer. If I tried to add a strong base to something that without a buffer, that would make it super basic. This time, because of that buffer, it just becomes slightly basic. Let's go ahead and try the opposite situation. So this time, again, thinking about our buffer here has our weak acid HA and our weak base A negative. This time, what happens if we add a strong acid? So remember, strong acids contribute positive hydrogens, and our weak base is just a negative. So this time, again, the opposites will react. So a strong acid will be reacted with our weak base, the opposite. And what you can see here is that these join up together to simply create HA. But look at that, HA, again, is something we already have in our buffer. Read it from the board for me. Tell me, what is HA in our buffer? HA in the buffer is just our what? It's more of our what? Thank you. I see Camilla. I see Shelves. I see Anthony. Read it. I'm literally pointing at it. Type it in the chat box. HA is just our what? Make sure you are participating. Yes, it is just our weak acid. So this time what we did is with our opposite, our weak base, we turned a strong acid into a weak acid by using the opposite weak base. Okay, go ahead and give me a green check, orange X if that's beginning to make sense. So by having both a weak acid, both a weak base in our buffer, we can take anything that's thrown at it and just turn it into the weaker version. All right, so this time, awesome, I'm seeing 10 green checks. Green checks if that makes sense, waiting on Timothy, Christopher, Alexis, Taylor, Kale, Omar, use that green check tool on the whiteboard, Canyon. Not asking for raised hands, just asking for green checks. Perfect. All right, looking good. So again, this time we just become slightly more acidic, but not super acidic like what would happen without our buffer. Now, why is all of this important? You're like, okay, Mrs. Larkin, that's great and everything, but why is it important? Well, buffers happen to be extremely important to your body. Without buffers in your body, you would die, okay? Your body has a very small margin for what is appropriate for your body. Think about, for example, with fevers and your temperature. If your temperature increases in your body by 6 degrees, it can kill you. Or vice versa, if it decreases by 6 degrees, that's hypothermia, that can also kill you. All right, so in the same way, buffers help to prevent your body from becoming too acidic or too basic. Case in point here, for your blood, as you exercise, your blood builds up excess hydrogen ions in it, which means it's becoming too acidic. H pluses mean acids. And so there's a protein in your blood called hemoglobin that can bind with those excess hydrogen ions and prevent your blood from becoming too acidic. Acidic blood, bad, because your blood should be slightly basic. So if it becomes acidic, again, you die, right? So buffers are extremely important. Same thing with your lungs. As you exercise, your lungs build up CO2 and lactic acid, both of which make your lungs more acidic. So buffers in your lungs help to balance that out and bring down that, bring it back to being more neutral, less acidic. And finally, your kidneys also help to keep acid-base balance in your body. They can excrete acidic urine or basic urine depending on if your body is too acidic or too basic. This is going to be number 5. Please go ahead and raise your hands when you have this saved. You have 30 seconds. Work fast. I have one last thing to talk about, and then we'll go ahead and let you go. Work fast. 25 seconds. Raise your hands. And apologies, I know New Row is tripping out right now, so just do your best. 15 seconds. Michael, Monty, Aria, Adriana, Daniel, Omar, Kale, Christopher, Timothy. 5 seconds. If you need to, take a picture. Waiting on Adriana. Omar in the chat. Kale. Christopher. Tim. Go ahead and raise your hands or chat with us. Thank you, Omar. I see you. Thank you, Kale. Thank you, Christopher. Adriana, Tim, let us know if you need help. Adriana, Tim. We'll go ahead and check in with you. Thank you, Adriana. All right, Tim, Mrs. Splivita will check in with you. All right, let's go ahead and keep on moving here. All right, so the last way in which we might use buffers is with antacids. Another important example. How many of you have ever had heartburn? Go ahead, give me a yes or no in the chat box. I, for example, rarely get heartburn, but I did actually get heartburn last night. Yes or no, how many of you have ever had heartburn? Yeah, so heartburn is not actually your heart. What's happening is stomach acid is coming up from your stomach into your esophagus, and it's burning your esophagus, which is what connects your mouth to your stomach. So it feels like it's your heart. It's actually happening in your esophagus, though, not your heart. Your mom yelled yes, Anthony. That's hilarious. Yeah, as you get older and your esophagus flap weakens, it becomes more common that you get heartburn. Anyways, so taking a look here, last night what I did is I took some Tums, all right? Whoa, that circle is way off. So I took some Tums, and what Tums do is they help to neutralize the acidity. So Tums have hydroxide ions, those are the bases, to help come in and neutralize the H pluses, the acid cations. And so this prevents your stomach from becoming too acidic. Now, your stomach should be pretty acidic. It has a pH of 2. All right, and it should stay around a pH of 2. But again, this is just going to kind of push it a little bit slightly higher so that it's not quite at 2, and this will help to prevent you from getting that stomach pain. However, the problem is antacids could make your stomach too basic. So for example, again, we want this to be pretty close to 2. So if it is pushed up to like a pH of 4, which is still acidic, but not nearly as acidic as your stomach should be, this could really hurt you, okay? So what happens here is a lot of these medications will also include buffers. And again, buffers don't necessarily have to keep things close to 7. In this case, they can keep things close to 2, close to what your stomach actually needs. All right, so just again, another real life example of buffers. Here we go, let's go ahead and wrap up.
And explained how buffers resist changes in pH and identify various buffers, hence the Rolaids. All right, so let's go ahead. We did this all through our 5B notes. Excellent job. If at this point you can turn in your 5B notes, then let us know how you did in the chat box. And